Assalamualaikum warahmatullahi wabarakatuh. So today we continue slide 35, 36, equation for rate of settling in centrifuge. New general equation for settling. If a centrifuge is used for sedimentation, removal of particle by settling particle, so attention moving heavily at its terminal and settling roughly the diameter of the smallest particle that can be removed can be calculated. In figure 30.2, this one can also refer to the books. In the books, this is based on Christy Jankowski. Frequent 2-2 one, page 1435. So the feed enter at the bottom. If you refer to 30.2-2, the feed enter at the bottom. And it's assumed that all the liquid move upward at uniform velocity, carrying solid particle with it. The particle is assumed to be moving radially at the terminal settling velocity Vt. The trajectory of the projection in figure 30.2-2, the particle of a given size is removed from the liquid with sufficient incident time is available for the particle to reach the ball of the wall. So to remove the particle, it must reach the ball of wall. Okay, so where it is held. The length of the ball is b meter. So at the end of the resident time of the particle in the fluid, the particle is at distance rb from the axis of rotation. If the rb is 1, it's less than 2, it's less than r2, then particle leave the ball with the fluid. If the rb is equal to r2, the particle is deposited on the ball of wall and specifically removed from the liquid. So 2 ways. Either the particle going out with the fluid or stick on the ball of ball wall. If it's less than R2, it goes to the liquid discharge. For settling in the stop flow region, the terminal velocity at radius R is obtained by substituting the equation to P.2-1. For the acceleration G into equation 30.1-9, then we get 30.2-8, where Vt is the settling velocity in the radial direction. Dd is a particle diameter. In meter. Rho D is the particle density in kg per meter cube. Rho is the liquid density, which is water. So this is rho for water. U is the liquid viscosity in Pascal second. If in that settling occurs, the right hand side of the equation 30.2-8, the right hand side is multiplied by the factor of epsilon square epsilon p given in equation 30.1-16. 30.1-16. 30.1-16 is, you can refer page 1418. So actually, yeah, this is the correction factor. Where the empirical correction factor these symbols is page 1417. Yeah, this equation, the symbols. The equation is the correction factor is epsilon 2, then this symbol epsilon to the square and multiply with this symbol. So this symbol is 1/10 multiplied by 1 minus epsilon, no? Epsilon. So the epsilon, or we call it volume fraction of the liquid, can be calculated using, there's no equation, but we can refer to example 30.1-2. This example, yeah, page 1418, 1419, 40, what 40? So 40% liquid divided by raw water over 40% liquid over rock water plus 60% solid over rock of glass pier. Okay, glass pier. And we get the epsilon. Okay. So if hindered settling occurs, then you need the factors. Since Vt is equal to dr over dt, then equation 30.2-8 become 30.2-9. Yeah. Meaning we substitute Vt to dr over dt. Integrating between the limits r equal to r1 at t equal to 0 and r equal to r2 at t equal to so Tt equal to 18 mu over omega square of t minus rho dt square down r2 over r1. Okay. So the resident time Tt is equal to the volume of liquid V in the bowl divided by the volumetric feet volumetric flow rate, volumetric cube per second. The volume V equal to pi b r square minus r1. Substituting into equation 30.2-10. Solving for Q, then we get 30.2-11 to determine the volumetric fit volumetric flow rate. The particle having diameter smaller than that calculated from equation 30.2-11 here will not reach the the ball of wall and will go up with the exit liquid. So diameter of particle is dp. dp. What's the dp? In meter. Larger particle will reach the wall and be removed from the liquid. So the way the centrifuge work is the particle should not mix with the outlet liquid or liquid discharge. It should stick on the ball wall. A cut point or critical diameter dBc can be defined as the diameter of a particle that reaches half the distance between R1 and R2. This particle move a distance of half the liquid layer or R2 minus R1 over 2 during the time this particle is in the centrifuge. The integration is then between R equal to R1 plus R2 over 2 at t equal to 0 and R equal to R2 at t equal to Tt. We then obtain QC. So at this flow rate QC particle with emitter greater than dPc will predominantly settle to the wall. And most of the smaller particle will remain in the liquid. So the cut point of critical limiter can be defined as the diameter of the particle that reach half the distance between R1 and R2. Yeah. This particle move a distance of half the liquid layer of R2 minus R1 over 2 during the time this particle is in the centrifuge. So refer back to the figure. So this is R1. This is the center to the feet. The R2 is from the center to the ball of wool. So DPC can be find as the diameter of reticle that reach half the distance between R2 and R1. So DPC is half the distance. Yeah. Minimum is R1. Oh, sorry, not R1. Uh, minimum between reach half distance between R1 and R2. This particle move a distance of half liquid layer. This is how you calculate R2 by R1 over 2. During the time this record is independent extension is 10 to then you have QC. Last 30.2-11 is for Q. This is QC. Refer to the critical diameter. Minimum diameter that allow the particle to reach the ball wall. A viscous solution containing particle with density rho p equal to 13 1461 kg per meter is to be clarified by centrifugation. The solution density rho equal to 801 kg per meter cube. And its viscosity is 100 centipoise. The centrifuge has a ball with R2 equal to 0.02225 meter, R1 equal to 0.00716. The height B equal to 0.1970 meter. Calculate the critical particle diameter of the largest particle in the exit stream if n equal to 3000 rev per minute and the flow rate Q equal to 0.002832 meter cube per hour. All right. Using 30.2-4, 30.2-4 is the rot is the tangential velocity of the particle. That's all. Angular velocity. So this is the angular velocity. Pi n over 60. N here refer to the rotational speed. Unit revolution per minute. So you get angular velocity in radial per second is 2 2010. The ball volume V is V equal to pi BR R2 square minus R1 square. So what is R1, R2? R2 is from the center to the ball. R1 is from the center to the layer, the first layer of the liquid. And it's CTPG. Viscosity mu. Okay, one is for water. Is it water? Oh, they didn't say. That is given in the question. The flow rate QC is 7.87. The information 30.2-12. 30.2-12 page 1436. Solving for DPC. Oh, okay. Asking how to to calculate DPC critical damage. So the DPC is 0.746 micron. Setting into question 30.2-13. So 30.2-13, if you refer to the book, page 1437, is special case for setting. For special case where the thickness of the liquid layer is small compared to the radius. Question 30.2-8 can be written for constant R into R2 and dP equal to dPc. Let's follow. So Vt, okay, no number. Oh. So equation 30.2-13 is for Vt only. Generating the real number setting in the stop law region, flow range. Eh? Then you calculate the real number and settling in the stop law range. Okay, so the question asking only until DPC. Yeah, until DPC. Ah. So to calculate for Reynolds number, use equation 30.1-17. So in the equation you need dP, Vt, rho, and mu. Centrifuge equipment for sedimentation. Tubular centrifuge. A schematic of a tubular ball centrifuge is shown in figure 30.2-3. The ball is tall and a narrow diameter, 100 to 150 millimeter. Such centrifuge known as super centrifuge developed a force about 13,000 times the force of gravity. Some narrow centrifuge having a diameter of 75 millimeter and very high speed of 60,000 or so rev per minute are known as ultracentrifuge. Supercentrifuges are used for separate liquid-liquid emulsion. So in the lab, we have the centrifuge as well. And the idea is the same. This ball centrifuge, this ball centrifuge one in 30.2-4 is used in liquid separation. So the feed enter the actual compartment at the bottom, travel upward through a vertical space. But the feed is entering from the top. Yeah. Sure. Okay. The whole divide the vertical assembly into an inner section where most light liquid is present and outer section where mainly heavy liquid is present. This dividing line is needed to interpose in tubular and centrifuge. Okay. So this is the light liquid, the heavy liquid. This is the solid. Yeah. The heavy liquid flow beneath the underside of the disc to the periphery of the bowl. The light liquid flow over the upper side of the disc and toward the inner outlet. Any small amount of heavy liquid solid is thrown to the outer wall to remove solid that are deposited. Okay. So this is used for starch gluten separation, concentration of rubber and attack on tube separation. Centrifugal filtration. The theory, this is for equipment using centrifuge equipment for sedimentation. The third one is centrifugal filtration. So theory for centrifugal filtration. The theoretical prediction of filtration rate in centrifugal filter have not been too successful. The filtration in centrifuge is more complicated than without filtration using pressure differences. Since the area for flow and the driving was increased with distance from the axis, specific cake resistance may change markedly. Centrifuge for filtering are generally selected by scale up from tests or similar type of laboratory centrifuge using the slurry to be processed. For the sister, centrifugal filtration different. We have filter medium, this is filter cake, then the liquid here. The theory of constant pressure filtration discussed in section 24.2b can be modified and used where centrifugal force causes the flow instead of impressed pressure difference. So the way filtration occurs in order to pass through the water, through to permeate the water through the membrane, you need a force to push the water to go to pass through the membrane, then we get the clean water. So in this case, instead of using that force, they are using centrifugal force to create the pressure difference. So in order to allow the water to pass through, then there must be a pressure difference between here and here. And the clean water permeate. That is what the this is what they indicate by increased pressure difference. The equation will be derived from the case where a cake has already been deposited, as shown in figure 2-5. The inside radius of the basket is r square. Ri is the inner radius of the face of the cake, and R1 is the inner radius of the liquid surface. We will assume that the cake is nearly incompressible so that an average value of alpha can be used for the cake. Also, the flow is laminar. If we assume thin cake is in a large spherical cylinder, then the area for flow is statistically constant. The velocity of the liquid is okay. So the filter medium is the filter itself. The filter cake is the solid that deposited that cannot pass through the filter. Over the time it will build up, then it look like a cake in front of the filter medium. So if the cake is very thin, then we can assume that the area for flow is constant, meaning We use the area of flow based on the filter medium instead of the neglecting the area for the cake. The velocity of the liquid is V equal to Q over A equal to dV over AdQ, where Q is the filtered flow rate in meter cube per second. And V, the velocity substituting equation 30.2-28 into 24.2-8. So negative delta Q equal to Q mu MC alpha over, okay. This is 30.2-29. Delta P refer to the pressure difference. Yeah, it should be pressure difference. For the hydraulic head of this DZM, DZM, DZM. At the hydraulic head of DZM, the pressure drop is dP equal to rho G dz in a single field. G is replaced by R or omega 2 omega square from equation 30.2-1 dz by dr. Then okay. The final equation is 30.2-33. So we go to the Q. So for the case where the flow area varies specifically with the radius, they're going to equation can be derived. Okay, 30.2-34, where A2 filter medium, area for the filter medium, AL logarithmic cake area, AA arithmetic mean cake area. So this is case of this is by point. It happened at certain time. So meaning this is not dynamic. So at time one, you do the calculation using 30.2-4. At time two, then you need to do another one based on the new condition, new information. If it's dynamic, then we need to do the integration. That's what we said. It's not an integrated function covering the whole filtration cycle. But this is where cases where the area for the cake, for the medium, for the filter medium, for the filter cake, it change over time. But yeah, for this book, it only cover not the dynamic, but we can say a static Q. Okay, next. Transportation metering of fluid. This is based on Yes, it's based on this book. Christy John Kiplis. Cerita apa? Hmm, ingat apa? It's okay. So, conversation and notary of lead. The topic, eh? Ah, this one is under CLO2. Introduction. We are going to learn about pipe and tubing, pump and compressor design. Okay, pump and compressor design. And then here, it's cheaper to transfer fluid than solid, either in form of slurry or a high velocity gas stream. And the substation pipe tubing, pump, fan blower, and compressor, people tube, and orifice meter. Pipe and tubing. Pipe is a heavily walled with large diameter and come in 6 to 12 meter length. Tubing is a thin wall, come in several hundred-meter long. So both pipe and tubing made from many materials such as wood, glass, ceramic, uh, metal, alloy, and plastic. So pipe versus tube. So for pipe less than 14 inches, so OD refer to outside diameter. So the OD must be for pipe that is less than 14 inches, the OD must be more than the NPS, and the NPS must be more than the ID. So pipe more than 14 inches, the OD is equal to the NPS. Or tube dimension always set by the OD WT. Buku tu. So buku piping. So pipe is based on the inside internal diameter, uh, inner inside diameter, For the tube is based on the outside diameter. Right. So Appendix A.5-1 is in the Gen Copley's book. This is the dimension of standard steel pipe. Steel pipe based on standard American practice range from 1/8 to 30 inches. Pipe of the material is also made according to steel pipe order outside diameter. Wall thickness of pipe is indicated by schedule number. We have schedule 10, 20, 30, until 160. But in table 8.5-1, the schedule number is only 30 and 30. So what is the difference between these two? It's the thickness of the pipe. So the higher the schedule number, the thicker the, the wall of the pipe. And we have tubing and table 8.5-2. So in appendix of the singular books, so for tubing, the wall thickness based on BWG, Birmingham wire gauge, Maelstrom 24, very light to 7, very heavy. Okay, the smaller the value, the thicker the wall, it's different from the pipe. The higher for pipe, the higher the schedule number, the thicker the pipe. For tubing, the smaller the number, the VWG number, the thicker the pipe, the heavier it's broken. Pipe selection. In large or complex process, piping system, the minimum size of pipe used for a specific situation depend upon the relative cost of capital, investment, power, and investment. For small information and sufficient accurate for a range of equipment that was shown in table 1. The liquid non-viscous liquid that offload inlet the pump. This is just an estimation. Estimation. Let the pump estimate 0.9 to 0.6 to 0.6 to 0.9. Process time at pump discharge is 1.7. For the viscous liquid, it's different. The gas and steam at 100 PSI. We have a joint fitting method to join pieces pipe of tubing. For screw fitting, the pipe and are threaded externally. The threading will weaken the pipe wall, while fitting normally weaker than the pipe itself. A pipe larger than 2 inches, normally connected by a flange or welding like this. This is the flange, this is the welding. Flange are matching this. So you have two flange, connect it, then bolt it with in the hole. So between the flange, there's a gasket to avoid leakage, of course. Connecting large pipe for high pressure is usually by welding. Allowance for expansion. Pipe of high temperature line could expand and contract. If fixed to the support, it could tear, break, or bend. For larger pipe, the pipe rests on roller and hung above by chain and rope like this. This to put it something new. Okay, pump. Oh, okay, okay. Pump installed in a pipeline to provide the energy needed to draw liquid reservoir and discharge a constant vertical look at the exit of pipeline ZP above the level of liquid. At pump, liquid enter the suction connection at station A and leave discharge at station B. In pump, the difference in height for suction in discharge is negligible. So if HA refer to the total suction heat, HB is the total discharge heat. So delta H equal to HB minus HA. So WP shaft work by pump and N is the fractional efficiency. So HB minus HA equal to over fractional efficiency. Pump requirement, suction lift and cavitation. The power supply by pump drive from external source noted as PV with M is the mass flow rate. So PV equal to M here equal to the mass flow rate with dot here multiplied by WP, which is the shaft work. So where do you see the shaft work? Normally you counter it in energy balance as well. Calculate the energy balance for the mechanical energy balance. The power delivered to the fluid denoted by PF equal to M delta H or PB equal to PF over M. If suction pressure is slightly greater than vapor pressure, some liquid may flash to vapor. Inside the pump, a process called combination that lead to severe erosion. So the vapor pressure you can refer to, you can calculate it using Antoine equation. Antoine equation, you need to refer, I'm not sure about this book. Antoine equation. Because for Antoine is based on the wait, there's a equation. There's a value A, B, C. You can refer to energy balance book, elementary to elementary or chemical engineering. In that book, yes, we have this calculation for the vapor pressure. So if the suction pressure is slightly greater than the vapor pressure, pressure refer to the vapor pressure of the liquid. If it's water, then vapor pressure of the water. Some liquid may flash to vapor. If the suction pressure less than the vapor pressure, there will be vaporization in the suction line. No liquid can be drawn into the pipe. So to prevent cavitation, the pressure at pump inlet must exceed vapor pressure by certain value. called the net positive suction head, or NPSH. So the pressure cannot be more than the vapor pressure, but and cannot be less than the vapor pressure. It must be exceed certain vapor pressure, certain value, which we call NPSH. Mm. Mm-mm. The required value of NPSR. The required value of NPSH is about 2 to 3 meter for small centrifuge pump, or 50 meter for large pump. Dimension, capacity, and weight of steel pipe. Okay. Is it similar to table A5? Oh, it's different. Oh, okay. Mm, it's the same. So this is in, yeah, this is in inch. Okay. The unit is continue. Example. Okay. For pump taken suction from reservoir NPS separated by NPSH produced OG. K minus TV over rho minus HSS minus ZE. Thank you very much. Mm. Okay, thank you very much. Yeah, that's enough. If you refer to this book, McCaptil, they are using English unit. See, PA prime is the absolute pressure at surface of the reservoir. PV is the vapor pressure of the fluid the pump would like to transport. HFS is the friction. Example 8.1, benzene at 100 degree Fahrenheit comes to system in figure 8.1, 8.5. Oh, okay. Sedang ya. Please. This is based on McCaptil book, chapter 8. Eight, which edition? The fifth edition. Is this the figure 8.5? Yes, this is the figure 8.5. The reservoir atmospheric pressure, the coach, uh, the coach pressure at the end of the discharge line is 50 pound per inch square. The discharge is 10 feet. and the pump suction profit above the level in the reservoir. The discharge line is 1.5 inch schedule 40 pipe. The friction in the friction line is known to be 0.5 pound cross per inch square. And that in the discharge line is 12.5 pound cross per inch square. The mechanical efficiency of the pump is 0.6% or 60%. The of benzene is okay at 65 kb per meter. Over pressure at 37.8. Over pressure of the for the benzene is 3.8 or 26.2 kilonewton per meter square. Calculate A. The developed head of the pump will be the total power input. See if the pump is specified in MPSHR. R requirement of R in here refer to required. Often will the pump be suitable for this service of that. So refer to question 4.32. The upstream session A is at the level of the liquid in the reservoir. And downstream session B is at the end of the discharge line, as shown in figure at 25. Figure at 25. Okay. From here, pump go to the B, bawah ke atas. Yeah. So when the level in the tank is chosen as the datum of height, it's noted as VA equal to 0. So this is the datum, the surface of the reservoir. So the datum is important to determine the height for the B outlet, the pump, and the inlet here. Okay, using this equation, the TVB is found by using data from 1925. So 1 inch, 1.5 inch PB40 velocity of 1 feet. Check that again. 1 feet per second correspond to a flow rate of 6.34 gallon per minute. Oh, this one, yes. Is it the velocity is 1 feet per second? Okay. So if the velocity is 1 feet per second, it will correspond to a flow rate of 6.34 gallon per minute. Can equal to this 1.5 here, schedule for T, 6.34 capacity at 1 feet per second. Velocity in S gallon per minute is 6.34 gallon per minute. So VB equal to T divided by 6.34, that's 6.31 feet per second. So the 40 here refer to the 40 gallon per minute at the output. With alpha B equal to 1, mission potential to give shaft work 1.5, 159.9. concourse over a pound. Like question 8.3, shuffle. Yes, shuffle plus expensive C. Yeah, so it's also the developed head. So delta H equal to HB minus HA is equal to this value. Refer to equation, this equation. So this equation is developed head of the Next is the mass flow rate. So the mass flow rate is 50 times 54 divided by 7 times 8 times 60. Refer to this equation. Yes. So the number. The power input from equation 8.4. This is referring to books by McCaptein. And we get power input. Total power input is 2.33 horsepower. Next is what is it? Total power, sorry, NPSH. So using equation 8.7, PA, absolute pressure at surface of the reservoir, divided by V rho, when the vapor pressure correspond to the head is 10.1. Efficient section line, HF, and value of efficient 8.7. See the last one. Swimming G over GC1, then NPSH is 22.77 feet. The available mass is usually larger than the minimum required value of 10 feet, so the pump would be simply for the purpose of this. So minimum or required NPSH is 10 feet. If the pump can produce more, it's suitable for the purpose. So the service here is to transfer water here, using pump to here, ZB. Yeah. That part is okay. Too low. Eh? 10 feet, yes, 10 feet. Okay, we continue the next class. Thank you.